Welcome to the Explainer. Today, we're diving into KSSM Form 3, Chapter 7 to uncover something pretty mind-blowing. How exactly do architects and engineers capture massive, three-dimensional realities on flat, two-dimensional paper? If you've ever looked at a towering skyscraper or a complex piece of machinery and wondered how it all started as a simple blueprint, well, you're in exactly the right place. We're going to decode that visual language today. Okay, let's take a building blocks approach for this. We'll start with orthogonal projections, move into drawing projections, then tackle plans and elevations. After that, we'll hit the four-quadrant method, translate from 2D back to 3D, and finally wrap up with essential rules and revision. Let's jump right into part 1, orthogonal projections. This is our foundation. Literally every architectural drawing out there starts with a plane. You can just think of a plane as a flat surface of an object. Now, there are three main types we'll be dealing with in this chapter: a horizontal plane, kind of like the floor, a vertical plane, like a wall, and an inclined plane, which is basically a slanted roof. This plane is essentially our canvas. So, to project a 3D object onto that 2D plane, we first need to understand what a normal is. And no, we aren't talking about typical behavior here. In drafting, a normal is a straight line that is strictly perpendicular to any line on the plane. Put simply, it forms a perfect right angle, exactly 90 degrees straight to the surface. And that right there brings us to the absolute core concept of this entire chapter. An orthogonal projection only happens when the image formed on a plane comes from projected lines that are strictly perpendicular to that plane. That means every single line shooting from the object's corners down to the paper has to hit it perfectly straight on, following those normal lines we just talked about. But you might be wondering, what happens if our viewing angle is a bit off? Like, what if those projection lines traveling from the object down to the plane are not perfectly normal or perpendicular to the surface? Well, the answer is pretty cut and dry. The image formed is simply not an orthogonal projection. If that angle isn't exactly 90 degrees, your resulting image gets distorted. It basically becomes an invalid drawing under the strict rules of engineering that we're studying today. In this world, accuracy is everything. Moving on to Section 2, Drawing Projections. Let's look at the step-by-step logic. If you want to draw this correctly, there's a strict four-step process you need to follow. First up, you've got to identify your viewing direction and the specific plane you're projecting onto. Second, draw your normal lines from all the vertices, the corners, of the 3D object straight down to the plane. Third, connect those intersection points on the plane to form your basic 2D shape. And finally, step 4, redraw the whole thing with true, actual measurements, making sure to clearly label all the vertices and side lengths. Now, here's where it gets really fascinating. Pay attention to the rule of what changes and what stays the same during this projection. Depending entirely on your viewing direction, the lengths of sides can actually vary. For example, a 10-centimeter inclined edge on a 3D shape might project flat onto the paper as only 6 centimeters. Wild, right? But, and this is a big but, a 90-degree right angle on a flat surface, that will always remain completely unchanged no matter what angle you view it from. All right, Section 3, Plans and Elevations. This is our core vocabulary. First up, let's talk about the plan. Think of a plan as exactly what a bird would see if it were flying directly overhead. It's the orthogonal projection looking straight down onto a horizontal plane. So anytime a blueprint or an exercise asks you for a plan, just tell yourself, okay, I'm drawing the top view. An elevation, on the flip side, is your view projected onto a standing vertical plane. This is literally what you see when you're looking at an object directly from the front or straight on from the side. We call these the front elevation and the side elevation, and they both live right there on vertical planes. So when you're actually drawing these out, there is a crucial visual code you need to use to communicate depth and shape. We use thick, solid lines for all the visible sides and edges that are facing us directly. Then we switch to dashed lines for our sort of X-ray vision. These show the hidden sides or interior features you can't quite see from your current angle. And lastly, we use thin, solid lines as construction guidelines to help us line up the final drawing perfectly. That brings us to Section 4, the four-quadrant method, synthesizing our views. Your viewing direction dictates absolutely everything here. It acts almost like a mirror. If your original 3D side view is looking from right to left, you actually draw the side elevation on the left side of your front elevation quadrant. And conversely, if your side view is from left to right, the side elevation goes on the right side of the front elevation. I know, it feels a little counterintuitive at first to flip it like that, but this cross-placement is industry standard, and it ensures your blueprints are perfectly aligned. By just following these 4 steps, you can use those thin construction lines we talked about to seamlessly connect the top, front, and side views perfectly to scale. Step 1, figure out your side view direction so you know which quadrants to use. Step 2, draw your full-scale plan in the bottom quadrant. Step 3, project those thin, solid lines straight up from the plan to act as a perfect width guide for your front elevation. And finally, Step 4, project lines from your plan across to a 45-degree angle line drawn from the center, then bounce them upward to intersect with the front elevation lines to complete your side elevation. It is honestly such a beautifully systematic process once you get the hang of it. Okay, Section 5, from 2D to 3D. Let's reverse the magic.
Working backwards from flat plans is incredibly satisfying. First, you just sketch the 3 flat orthogonal projections floating on their respective planes based on the measurements you're given. Next, project those flat surfaces inward through space until they intersect. Then, using those intersections as a guide, you sketch out the final solid 3D shape, making sure to diligently label every single vertex with its corresponding letter. Round it all off by labeling all the true side lengths, and boom, you've built 3D from 2D.
And finally, Section 6, Essential Rules and Revision, your keys to success. Let's do a quick rapid-fire recap. Remember, in orthogonal drawing, accuracy is king. Always use actual, accurate measurements. Diligently label all your vertices. Stick strictly to the visual code. Solid lines for visible edges, dashed lines for hidden ones. Trust your thin construction lines and that super helpful 45-degree projection angle to keep everything perfectly aligned across quadrants. And always remember, while right angles usually stay exactly the same, inclined lengths will project differently than their true physical length. Mastering these foundational projections literally gives you the superpower to translate pure imagination into physical, constructible structures. So, I want to leave you with this exciting thought. If this mathematical secret code lets us build reality from flat paper, what will you design next? Thanks so much for exploring this fascinating topic with me. Keep practicing those normal lines, and I'll catch you in the next explainer.